Hello everyone. First of all, I would like to take this opportunity to thank the organizers of this seminar for their excellent job and management. It's my pleasure to introduce Professor Fatemeh Beik for the next talk, which is also the last talk of this seminar. She received her BSc degree from Valias University of Rafsanjan and MSc degree from Shahid Bahunar University of Kerman. She also received her PhD degree from Shahid Bahunar University under supervision of Professor Mohseni Muqaddam in 2010. At present, she is an associate professor of mathematics at Valias University. Her research interests are mainly iterative methods and preconditioning techniques, tensor computations, network sciences. She has published more than 30 papers in major journals such as Science Journal on matrix analysis and application, numerical linear algebra with applications, applied numerical mathematics, linear and multilinear algebra, and many others. She is a winner of Professor Riazi Award for the best paper presented in 74th Annual Iranian Math Conference. And now she is also a winner of Professor Rajab Alipur Prize. She spent a year of sabbatical leave at Emory University hosted by Michele Benzi in 2016. At present, she is an editor of Bulletin of Iranian Math Society and three other journals. And finally, she has supervised 3 PhD theses and 11 MSc dissertations. The title of her talk is a survey on preconditioning techniques for double saddle point systems, spectral and field of values analysis. Professor Beik, please.
Can you hear me? My voice is clear. Okay, that's great. Okay.
Yes, we can. We can start. But your PowerPoint
Okay, hello everyone. At the beginning, I hope you all have been doing well during the pandemic, and hopefully things will get better soon. I'm also so thankful to the organizer for the kind invitation, and I'm honored to present this work in such a nice seminar. Alright, let's get us started. Today I'm going to talk about the two kind of tools which help us to analyze the performance of the preconditioners. In particular, I'm going to talk about preconditioning techniques for double saddle point systems. Here are some acknowledgements before going to the main discussions. This is a joint work with Michele Benzi, and a special thanks goes to Alison Ramage and Eskal Dadenheim for providing us the test problem. I should point out that this is a work which is still in progress, at least in numerical experimental part. We need to try out several other ideas. So if you have any questions about the details of the proof, you can send me an email. Let me start with the kind of a brief and simple review on the concept of preconditioning. We have a linear system of equations, Ax equal to b, where A here is non-singular, and we are considering the problem that comes from discretization of PDE. So A is also sparse and large. And in a very simple way, we can say that preconditioning means that we are going to solve an equivalent linear system of equations instead of the main problem. I gave here for you the right preconditioning techniques as a second linear system, in which the matrix P inverse acts as a preconditioner, and it's beneficial to consider it as an approximation of the inverse of A. We are interested in applying plot subspace method, and we're going to propose preconditioner, and the hope here is that we can accelerate the rate of convergence of these methods. So we need some tools, right, to analyze the performance of the preconditioner. I'm going to talk about two kind of tools here, spectral and field of values analysis of the precondition matrix. Here the matrix A times P inverse is called the precondition matrix, and I should point out that we are not going to form this matrix. And one of the main points of this presentation is that when does someone need to go from spectral analysis of the precondition matrix to field of value analysis, I mean for the application that we are going to consider here. Okay, we're going to solve this linear system of equations in which the first two blocks in the main diagonal are both symmetric positive definite matrices, and the matrices A21 and B transpose have full column rank. This kind of linear systems appears in finite element discretization of coupled-Stokes Darcy flow problem. For more details, we can see the following two works. In these works, several types of preconditioner were examined. Here, I brought for you the best one. In the JCAM paper, I mean the first paper, the author worked with this, let's say, block lower triangular preconditioner. In the third block, the matrix M sub P is the mass matrix, which is spectrally equivalent to the Schur complement of a Stokes operator. And the mass matrix corresponds to the Stokes operator, the pressures of the Stokes equation. And one can expect that mass matrix is going to provide an approximation for the Schur complement BA22 inverse B transpose. We are going to see that. For further details about the properties of the mass matrix, you can see the following book. In the second work, I mean the work in the FISC, the author worked with the class of constraint preconditioners, the diagonal and triangular one. Here I gave the partition to make it clear what the word diagonal and triangular refer to. It's difficult to see that the previous linear system of equation is equivalent to a kind of different linear system, which is called double saddle point problem. It also arises from other applications, which is mentioned in the first reference. We also worked on that problem and proposed several kinds of preconditioner in our SciMax and Chalcolo paper. This is the coefficient matrix in the paper by Allison and her collaborator. Here we call this double saddle point system because if we consider this partitioning, the first block is in fact the coefficient matrix of a saddle point problem. The name is basically given by Michele for this kind of system. If we define the orthogonal matrix X, and you can see that the matrix A is similar to matrix A sub 1, then you can drive the matrix in blue color, which is in the form of the matrix in the work by Allison and her collaborator. So this shows that the previous linear system is equivalent to a linear systems which have this kind of coefficient matrix, I mean, with this structure. For the condition, so that ensures the non-singularity of the matrix A, we can refer, for instance, to the Chalcolo paper. Let me list some conclusions from the FISC paper, which came after the JCAM paper. We are solving a linear system of equations which correspond to a discretization of the PDE, let's say. In case that the domain of the problem is two-dimensional, then the sparsity patterns of the matrices is nice enough to implement the preconditioner exactly. What do I mean by exact implementation? Well, inside the GMRS, you're going to apply the inverse of each preconditioner, right? P inverse, right? So you end up solving some subsystem. In case that you solve the subsystem exactly by means of direct solver, then this is exact implementation. In this case, based on the result in the FISC paper, one can see that the triangular constraint preconditioner outperforms other preconditioners when we use them with GMRS. It has some reason, I'm going to comment on that. Basically, this is something that we can expect from the theoretical part of the paper, because the author shows that the proposed preconditioner, I mean the constraint preconditioner, There are field value equivalent coefficient metrics of linear system. So geometry should show edge-independent rates of convergence based on theory. Nevertheless, in the case that the domain of the problem is three-dimensional, then the author only worked with the preconditioner in an inexact way, which means that they solved the subsystem inexactly by erratic method with, let's say, loop tolerance. In this case, they didn't report the result for the triangular constraint preconditioner, and based on the result, when you use the preconditioner with flexible geometry, I'm going to call it F geometry from now on. When they use diagonal constraint preconditioner, they get the best number of iterations. However, the preconditioner in the JCAM paper is more economical, of course, with suitable values of the positive parameter rho. In general, we can say that based on the result in the fifth paper, all the preconditioner in their inexact implementation experience some degradation in the rate of convergence, and the size of the problem goes up. Okay, here we are going to consider an equivalent linear system of equations. We have a term here. The linear system is called augmented linear system. We add a term here. Here R is a positive parameter, and we are going to consider this preconditioner, P sub R and alpha. Here, I use two parameters because I want to report on the result for the case that R is equal to 0. Alpha is always positive, and Q is a matrix which is positive definite, symmetric positive definite, and it is given. I should point out that one can consider more general cases. However, here we limit ourselves in a case that R is either equal to alpha or it's equal to 0. Okay, let's move on to the eigenvalue analysis part. Why do people analyze the eigenvalues of the precondition metric? Well, the precondition linear system is a kind of linear system of equations. So let me talk about linear system of equation in general. If you have a linear system of equation x equal to b, where a is symmetric, positive, definite, then if you can show that the spectrum of the matrix A is well clustered, which means that the eigenvalues belong to a small interval, then you can expect that the gradient is going to converge very fast. However, in general cases, when the matrix is non-normal, the situation is more complicated. Okay, however, if the matrix is close to be normal, then a well-clustered eigenvalue distribution away from 0 may result a rapid convergence for the geometry. For more details, you can see this survey paper of my collaborator. In the next slide, I'll show you some bounds for the eigenvalues of the preconditioned system. Here, I should point out that in this paper, they didn't derive the eigenvalue bounds. However, as you can see here, I'm going to comment on that. For this application, it's beneficial to analyze the eigenvalue distribution too, because it sheds light on the field of value analysis too, right? Okay, let's move on. I'm going to talk about this later more. First, we consider constraint preconditioner. For the triangular constraint preconditioner, the precondition matrix has all the eigenvalues of the precondition matrix are real and positive, and basically we can see that the spectrum is a subset of this interval. You see the fraction here, right? This is something that is useful to make some guess, which is basically true. For the diagonal constraint preconditioner, we can see that all of the eigenvalues of the precondition matrix are complex, and again we have this bound for the imaginary part. We see the fraction here again. So based on the eigenvalue analysis, we saw that the problem has basically this property. This means that A22 minus this matrix A1, A sub 1, 2 transpose, blah, blah, blah. Yeah, this is symmetric positive semi-definite. And this was helpful. This is something that we found from eigenvalue analysis and tested the problem numerically and saw that we actually have this property and even stronger than this property. By setting this assumption, we could see that the eigenvalues of the precondition matrix is well clustered away from 0, and also we could derive this bound for the absolute value of imaginary part of eigenvalues. Also, we could see that numerically, for suitable parameters, suitable choices of the row, like row equal to 0.6 or 0.7, we have even this stronger assumption. And this is something interesting because if you have a look on the JCAM paper, you see that the author experimentally found that this parameter is suitable. And we have this assumption for this parameter. So if we set this assumption, we can prove in theory the fact that the author observed in their paper numerically, they plotted the eigenvalue distribution, but they didn't derive the eigenvalue bound. Here we can do that by setting this assumption that we found from eigenvalue analysis. So for proving this result, we use the following theorem and some of its extended version. For our proposed preconditioner, for the augmented linear system, we could see that the eigenvalues of the precondition matrix are all real and positive, and basically the spectrum is a subset of this interval. And if we set that assumption, here we can see that the eigenvalues belong to this interval 1 and 2 when R goes to infinity. It turns out in the proof that most of the eigenvalues goes to 1 as R goes to infinity, R goes larger. In proof, we could see that if lambda is an eigenvalue of the precondition matrix, then with the corresponding eigenvector in this form, where here we assume that y is not in the kernel of B, then the eigenvalues satisfy in the following quadratic equation, where gamma and eta are given as follows. Considering the definition of A hat to 2, we can see that gamma goes to 2 and eta goes to 1 as R goes larger. So all the eigenvalues goes to 1, most of the eigenvalues, because we have the assumption that y is not in a kernel of P. So most of the eigenvalues goes to 1 as R goes to infinity. Nevertheless, it's not recommended to work with very large values of R, because in most of the cases, most of the applications, we end up solving two-way condition subsystem corresponding to second block, and this means that we're in trouble. So even we shouldn't work with large values of parameters. And we observe that with model values of R, like R equal to 10, we can derive good results, at least based on the number of iterations, right? Required number of iterations for the GMF to be convergent. We have also a metric Q based on the theoretical part of our work. We could observe that if a suitable choice for the matrix Q is the mass matrix. We could also see that the diagonal of the mass matrix is going to provide an efficient approximation for the mass matrix when we plot the mesh of the mass matrix with MATLAB. Here I plot for you the eigenvalue distribution of the precondition matrix in blue colors, and we see the theory numerically. When R go larger, then the eigenvalues are clustered around 1 more and more. Okay, in this part, I'm going to give you a brief review on some convergence result in the literature for the crowd subspace method. This part is for those who are not doing research in this field. And actually, I want to answer this question: why spectral analysis of the precondition matrix is not enough, right? So we have a linear system. Basically, we consider the case that the linear system comes from discretization of PDE. So it's large, sparse, and non-singular. We assume this. We have this assumption. The current subspace method approximates the exact solution at a step k, let's say, in this form. I mean, P of A times P is the approximation. And here, P is a polynomial of degree k minus 1. And its coefficients are determined in a way that the normative residual corresponding to this approximation satisfy an optimality condition. For instance, if A is Hermitian, we can consider midrest and conjugate gradient. I'm going to call it CG. For the CG, we also need another assumption. A should be positive definite. Each of these methods minimize different normative residual at a step K. Both methods find the approximation in the first subspace, let's say with initial guess 0, and but they minimize different norms. For midrest, we minimize the Euclidean norm of the residual, while in the CG, we minimize these weighted norms of the residual. Here, one can see that eigenvalues of the matrix A, which is Hermitian, are descriptive for the convergence behavior of the midrest and CG. So, if you have a well-clustered, basically, eigenvalue distribution, then these methods are going to converge fast. So, in general, to have well-clustered eigenvalue, you have to apply a preconditioner. So, if you want to talk about eigenvalue distribution and your precondition matrix is Hermitian or Hermitian positive definite, then again you are done if you can say that my precondition matrix have a spectral clustered spectrum away from 0. Basically, we have these two bound in the literature. For the further details, you can refer to Yusuf Saad's book, for instance. These are too technical. Let me give you another formulation, which is more tangible for those who are not doing research in crowd subspace method. For the second inequality, we have this formulation. As you can see here, this condition number, because A is symmetric positive definite or Hermitian positive definite, can be given with this fraction. So, in case that we say that the eigenvalues belong to a small interval away from 0, this means that lambda mean is very close to lambda max, and so the condition number is very close to 1. So we can expect very good convergence speed for the CG, right? And also for the midrest, as I mentioned before. So in general, the eigenvalues are descriptive for these methods. So in more general cases, when the matrix A is not Hermitian, then we are going to use GMRES and minimize the Euclidean normative residual. Here, the theories are not as nice as the case of the matrix is Hermitian. For example, if A is diagonalizable, then we have this bound. In case that the matrix is unitary diagonalizable, which means that A is normal, then this condition number of X is equal to 1, and you recover the result for the midrest. So again, you're done. If you can say that I propose a preconditioner and my precondition matrix is normal, so when you say that the eigenvalues are well clustered away from 0, then the GMRES is going to converge fast. However, in case that the matrix, or the precondition matrix is not close to be normal, the situation is more complicated. Considering this work, the author basically showed that with prescribed eigenvalues and any non-increasing sequence of positive numbers, right? If you have, they can construct for you a matrix, a kind of n by n matrix, and the right-hand side B, so that if you apply the GMRES with initial guess 0, you get this norm for the residual. So this is terrible, right? So this shows that if you have a well-clustered eigenvalue distribution for the precondition matrix, let's say all of the eigenvalues are equal to 1 and your precondition matrix is far away to be called normal, let's say, then we're in trouble. So what should we do? At least for our mainstream application, the problem that comes from this visualization of PD, there is something that can be helpful. Let's go to the field of value analysis part. Here, we talked about two notions, norm equivalence and field of value equivalence. These are can be used, these notions, to talk about convergence behavior of GMRS and to talk about optimal condition for the proposed precondition. And for further details, we can see the following two works. We call two matrices M and N H norm equivalent if we can find constant alpha sub 0 and beta sub 0 which are not dependent on the size of the problem, and we can show this inequalities, right? Here the matrix H is a given symmetric positive definite matrix. So if you want to prove this property, you should say that what is the matrix H. Another stronger condition, we have two n by n matrix. We call them H field of value equivalent. If we can find constants which are not dependent on the size of the matrices alpha sub 0 and beta sub 0, such that the following two inequality holds. In the following works, it has been shown that if we have two matrices which are H field of value equivalent, it's basically M inverse, the H field of value of M inverse is bounded away from 0. Here is the H field of value of the M inverse. Basically, it's with respect to a kind of weighted, product. It's field of value, it's nothing new. In this slide and the next one, we can see that the notions of norm equivalence and field of value equivalence are both descriptive for the convergence of mean breadth and GMRS. Let us consider linear system of equation with coefficient matrix M, and we propose the preconditioner N. If we can show that M is H norm equivalent with a certain inner product, let's say, with the preconditioner N, and we have this assumption that M times M inverse is symmetric and generally indefinite, right? Then the mean breadth for solving the linear system with coefficient matrix M and with the preconditioner N converge in a number of equations which is not dependent on the size of problem. Here we have this bound for the convergence of the mean breadth, for the relative residual norm error, we have this bound, and the important thing here is that in this bound, alpha sub 0 and beta sub 0 are not dependent on the size of the matrices M and N. And it's clear that if alpha sub 0 and beta sub 0 are close to each other, then we have a fast convergence speed. For the GMRS, we need a stronger condition. The coefficient, the proposed preconditioner should be H field of value equivalent coefficient matrix so that GMRS with the proposed preconditioner converge a number of iterations which is not dependent on the size of the problem. And it is proved that for the we have this bound for the relative error of the norm of residual. The important thing here again is that in this bound, the parameter alpha sub 0 and beta sub 0 are not dependent on the size of the matrices N and N. For further details about this bound, we can refer to the following two works. In summary, if we have a linear system of equations and we propose the preconditioner, and then we could show that our proposed preconditioner is field of value equivalence with a certain inner product with the coefficient matrix of the linear system, then if we apply GMRS with the proposed preconditioner, then we can expect a convergence behavior which is not depend on the size of the problem or on the discretization parameter, because we consider the problem that comes from discretization of the PDEs. For the constraint preconditioners, in this paper it has been already proved that the proposed preconditioner are tilde value equivalence with the coefficient matrix of the linear system. In order to start the tilde value analysis, we need this stability condition to be held. This is something that the person that discretized the problem should tell you, that whether in a way that they use the finite element method for discretization, the linear system, I mean the coefficient matrix of the linear system has this property or not. This was an assumption in the CIS paper and also in the JCAM paper. So we again have this assumption here. Here the parameters C sub 1 and C2 are not dependent on the size of the matrix A. And the matrix H is given as follows. The challenge for us, at least for me, was that to show that the stability condition holds for the matrix A hat, because we are solving an equivalence system. And with some algebraic computation, we finally could prove that. And I should point out that at the very first step of this work, we've done the tilde value analysis for the case that alpha is positive but R is equal to 0, right? So after some algebraic computation, so we could show that by having the stability condition for the main linear system, then we can prove that similar to the stability condition for the matrix A hat, which has for the augmented linear system, right? And finally, the main problem I present for you, these are actually for more than 10 pages of the proof. I brought here the main theorem here because these are too technical. Here is the main results. Our proposed preconditioner is H inverse, and H was that black diagonal matrix that I showed you in before. I mean, that's A11, A22, and M sub P is in the diagonal, and here is H inverse. So the proposed preconditioner here is H inverse till the value equivalence with coefficient matrix. I have some comment on this condition, which is a little bit technical, so I would be happy to take any question on that. But for this condition, I want to talk a little bit about this one, which says that the matrix A bar is H1 inverse till the value equivalent to P bar, which was its, I think it was the upper triangular part of A bar. A similar assumption was assumed in a physics paper. I mean, the matrix A is H1 inverse till the value equals to its lower triangular part. I should point out that while doing the eigenvalue analysis, we found that for this application, we actually, for the blocks, have these properties, right? And based on this property, we could derive some assumptions that imply these two assumptions, right? We proved this result. We set here this assumption and this one, which is hold for the problem that corresponds to discretization of the coupled sub-Darcy flow problem. We set this assumption, and here we said 3 divided by 4. I mean, it's weaker than 0.5 even. And we could verify that if we have this condition, I mean, the parameter R is chosen in a way that this inequality holds, then we can conclude the assumption in the theorem. Note that if I set R equal to 0 here, this is something that always holds because lambda sub m is the eigenvalue of this matrix here. I wrote here, right? So this is a symmetric positive semi-definite matrix. So this one is always non-negative. So the assumption in the CIS paper as a whole, we need to choose the parameter R in a way that we have this inequality. Right? Okay, let me add some comments about the concept of optimal preconditioning. We're solving a problem that comes from discretization of PDEs. So with respect to different discretization parameter, we basically have a sequence of linear systems. And we are going to propose a preconditioner. So in case that we could prove that our proposed preconditioner is fit of value equivalent to the coefficient matrix of this linear system, we basically could see that GMREF with exact implementation of this preconditioner shows a mesh-independent convergence behavior, because that bond, on that bond, the alpha sub 0 and beta sub 0 were not dependent on the size of the problem. So if we can implement the preconditioners in a way that the cost of applying the preconditioner is linear in the number of POF, then we can call our proposed preconditioner optimal, right? Okay, some numerical experiments. In all of the experiments, we constructed the right-hand side of the linear system in a way that the system has a random solution, because we wanted to monitor the accuracy of the solution. And we run the code 10 times and then took average and reported results here for you. We used FGMREF. There's no restarting here. And all the implementation are in an exact way. That is, inside the FGMREF, we have some iterative solvers. This notation iter means the author iteration for the FGMREF, and iter sub PG or PCG means the whole number of iterations inside the FGMREF. Let me first report results for the Allison problem. Here there is no augmentation, that is R is equal to 0. The matrix Q is basically the Schur complement, right? But we are not going to form that. In our SciMax paper and also in Calculo paper, we talked that BA2 to B transpose is going to provide a good approximation for the matrix Q inverse. This is a guess by Michele, in fact, and it works perfect because when we solve the corresponding linear system with coefficient matrix Q with precondition conjugate gradient with this preconditioner BA2 to B transpose, then it converts very fast, right? It is so efficient, the preconditioner. Here my system for the first example, stopping criterion, and the details of implementation of the preconditioner. I'm going to move on fast to save time. Here, the matrix A11 and A22, we solved the corresponding linear system exactly, but for this one, BA22 inverse B transpose, we use PCG with the mentioned preconditioner. Here are the results. We can see that if we use FGMREF with this preconditioner, I mean construct triangular preconditioner, it works better in terms of the required number of iterations. But for the other preconditioner, we can see that it is more economical, let's say. The times are better. The reason is that at each iterate of the FGMREF, when you apply this triangular construct preconditioner, you have to solve one extra linear system. Okay, let's move on to the harder problem. The problem in this fifth paper, right? We consider that the case that the domain of the problem is three-dimensional. I had to work with another kind of system which is stronger than my system. Here is the stopping criterion, which is exactly the one that's used in this paper. In this case, all the subsystems, I mean this one with this coefficient matrix, are solved with PCG and with low tolerance. I'm going to skip the details here to save time. And here iter sub CGI means that we are using conjugate gradients for the linear system corresponding to coefficient matrix A sub II. For the mass matrix, we use CG without any precondition because it's quite well conditioned. Whenever we use PCG, we use the Eichel factor with drop tolerance between 10 to minus 4 or to 10 to minus 2. Here are the results for the constraint preconditioner. As you can see, the number of iterations in the inexact implementation when we use this precondition with FGMRS goes up. Here we expect the same thing. I should point out that the same thing happens in the CIS paper, but they use fixed number of algebraic multigrade solver and fixed number of iterations inside the FGMRS, but we use PCG, and one can see that again they experience the same phenomenon, but the growth of the number of iterations for them is moderate, but here is severe, right? However, unlike the result in the CISC paper, we observed that with this implementation for the preconditioner in the JCAM paper, the number of iterations is nice, right? It remained fixed somehow when we use the preconditioner with FGMRF. And for this one, P sub 0 and 1, we can see that the times are better. The reason is that here we have a linear system with coefficient matrix M sub P, that is the mass matrix, but in the other case, the coefficient matrix is diagonal part of the mass matrix, so it's cheaper. And I should point out that for the preconditioner in JCAM paper, we use the best scaling parameter rho, which is 0.6, right? If we work with other values, then you may experience weaker performance of the preconditioner. For our proposed preconditioner, for the case that we have the parameter R is positive, we consider two cases. First, we did not form the matrix, right, here. And then we use conjugate gradients. So we have to work with moderate values of R, basically, because to avoid the case that the matrix becomes ill-conditioned. Actually, the matrix is not that much ill-conditioned here, and we can use the CG when R is equal to, I guess, 2 and 5. In the second case, we form the matrix. This is not a full matrix, but of course we lost sparsity in comparison with A22. Then we use PCG and compute the preconditioner with the Eichel factor. I should point out that for larger problem, we had to add a kind of a small shift here so that the MATLAB can compute the Eichel factor. Here for the case 1, we have the best result. I gave the best times here with bold fonts for the second test problem. As you can see, the best time are for the case 1. The number of iterations increased a little bit, but the increasement is very small here. Here R is equal to 2 and R is equal to 5. And for the second case, we have very nice number of iterations, but the times are not good in comparison to the first case. The reason is that here we form the matrix, so it's a bit expensive in comparison to solving, in the case 1, right? Okay, some conclusion. We talked about two kind of tools mainly, which help us to analyze the performance of the preconditioners. We also presented some results about our work is still in progress, about some block preconditioners and our work actually. We talked about them, and we mainly consider the case that the problem comes from finite element discretization of coupled Darcy flow problem. Moreover, we worked and examined the performance of the preconditioners for another application. For that application, I mean the work by Allison and her collaborator, we could observe that all of the examined preconditioner are scalable. This means that FGMRAS solvers scale linear in terms of CPU time. I mean, it scales linearly the time when the dimension goes up. I mean, the size of the problem goes up. However, here I only report for you the best one for the first tested problem. For the second problem, our numerical experiments show that the proposed preconditioner with FGMRAS outperforms other preconditioners. In general, in theory, it has been proved that constraint preconditioner and the proposed preconditioner are field value equivalent to the coefficient matrix of linear system. However, in exact implementation, we see that all of the preconditioners are nearly scalable. In a special case, we can call these two preconditioners, I mean P sub 0 and 1, and this one J can paper optimal to be nearly optimal. Therefore, still we need to work
Thank you so
more
much,
on the
Dr. Beik, for
implementation
nice
of
presentation.
the preconditioner, so
Is
that
there
we
any
can call the
question?
preconditioner optimal, right? Still, we need to try out some other ideas for the implementation of our proposed preconditioner. For the future, also, one can use and examine the preconditioner for the problem that comes from discretization of coupled Navier-Stokes-Darcy system. This is a suggestion by Michele, and we have not started working on yet. Okay. That's it, everybody. I hope the best of all for you, and thank you for your attention.
Dr. Beik, could you see the question raised by Professor Greenbaum?
Okay, thank you.
Question written by Professor Greenbaum. Could you get a stronger convergence result using the Croce-Palencia result that FOV is 1 plus square root of 2 spectra? Okay, thank you. A question by Professor Musavi. Can you see?
That's a great suggestion. I need to work on. Thank you so much for your suggestion. The good thing that
Thanks
we
for
did
an
not
excellent
finish the work and
presentation.
it's
Sorry
still in
about
progress. Thank you. I should try it. I should work on it. I should think about it. I haven't tried this. It's a nice suggestion, right?
In slide 54, how do you form the inverse of a Q?
Yes.
On page 54.
I have no idea about that question. Yeah. What else? Dr. Rafi is typing. The matrix Q slide. You mean in numerical experimental part? This okay. 54. In the first case, we do not form the, and I should point out that this Q is the diagonal of the math matrix, and Scott gave us the math matrices. So this one is the Q inverse is a diagonal matrix, right? Because I pointed out that a suitable choice is the math matrix, but when we plot the mesh of the matrix, we observe that its diagonal is going to provide us a kind of efficient approximation. So it's quite cheap. So we let's say we want to multiply this by a vector. So in case that we do not form the matrix, we have B times X, let's say, and Q inverse. So it's quite cheap. In the case 2, again the matrix Q
Dr.
is
Musavi has a
diagonal. We
question.
form the whole matrix,
Do you have
right?
any information
And
about
then we
preconditioning
can use the
techniques for
actual
solving
factor.
large
As I mentioned
linear
here, for
systems
the
in
larger
finite waves,
problem, we have
for
to add a
example,
shift
GF2,
so that the math
where there is no
can use the
notion
actual
of
factor.
convergence?
Always, you have a Schur complement.
Thank you.
What when you have a Schur complement? I don't know.
It seems not,
This is approximation of the math matrix. That a kind of approximation for the Schur complement. For the Allison problem, actually we could work with Schur complement, but on that case, again you have a problem by finding the let's say precondition or for solving the subsystem in general cases.
Thank you all very much. And the closing program will be start about 20 minutes. After the closing, we will give another group photo. You are welcome. Now, we show a short clip about Kerma. Take a look at this.